It's been a while since the first LGOAP devlog. In a manner of speaking, it's actually been 1.5 years, and since then I have done so much more on the plugin. After two failed prototypes, one of them involving a massive C++ and C Sharp invoke interop toolset, I decided to just go ahead and use Unity's existing data-oriented toolset, mainly job system and the burst compiler. And I feel like I'm at a good enough place to showcase something. So, let's get started. First of all, I reworked the whole Blackboard system for a much smoother UI and strongly typed keys. The Blackboard system supports inheritance and instant synchronization. You can also mark a Blackboard key as essential to decision making, which will cause the system to rerun the planning algorithm. Still on the topic of Blackboard, I'd like to mention that the new system runs on a multi-threaded virtual machine that interprets bytecode. To that end, the system prevents you from entering play mode or building your project if your Blackboard templates or any other similar components that depend on the bytecode fail to compile. If you choose to modify the source code, I've also included some custom debugging tools such as this compilation registry viewer, which will show you which portion of a Blackboard template is compiled at which address. Moving on to the core, we have our actual planning system. In my original system, actions were tied to game objects, and the code to execute the said action was embedded within the game object. I quickly realized how bonkers an idea this was and abandoned it in favor of a planning domain, thereby centralizing the action execution. The dynamic runtime state is better represented using a Blackboard anyway. The new domains are a form of visual scripting that let you author AI. Coming to an actual example, here is the simplest form of a domain. It has one goal, one layer of tasks, and one task. Goals are selected based on their insistence, and the insistence can be calculated dynamically based on the Blackboard. Once a goal is selected, the planner then attempts to generate a plan that would satisfy the goal's target. The tasks all have their own preconditions, costs, and effects that can all be inferred from the runtime state of the Blackboard. Each task can have one or more task providers that will be executed in the sequence. These are modular, self-contained, data-driven states that can be scripted by a programmer, but can then be reused in more than just one place. Each task can also optionally have a list of services that are executed in parallel to the task. The difference between the two is that while a task provider is responsible for the duration of its runtime, a service only receives callbacks for when it's started, ticked, or stopped. For example, a task provider can be about moving to a target location or waiting for a number of seconds, while a service can be about setting the mechanism variables so the agent can play the locomotion blend space at the correct speed. We'll look at more examples in other demos, but for now let's take a look at how this particular domain plays out. The goal has no target and the task is set to always fail its precondition, but both are marked as fallbacks for the respective layers. Fallbacks will be used if for any reason a layer is unable to procure a plan. Because this task will never be valid, there won't ever be a plan, and so the fallback will always be used. And so this agent will keep on patrolling through the collection of patrol points. Let's take a look at that. But just patrolling is boring, so I made a perception system. It uses layer masked sensors and stimuli system. A stimulus is a point in the 3D space with an associated object and a type. A sensor is a shape in the 3D space with the types of stimuli it can perceive. Optionally, you can also take into account navigational distance or line of sight. Using the perception system, we can quickly author a slightly more complicated domain where an agent looks out for a celebrity character, gets excited, and can greet it. Staying at the same level of abstraction, we create a key in the Blackboard and a related goal in the domain. We look out for the celebrity while patrolling and update the Blackboard as relevant. We can see the high-level abstraction in full force because every greeting task automatically fails because the agent cannot contain its excitement. While it's trying to greet the celebrity, it will also track the celebrity's location. Let's see how that fares out. There's still something missing though. Until the other character responds, it's not especially dynamic. And so we can give the celebrity character its own optionally shy personality, where it gets creeped out by a fan if greeted too many times. To make this task easier, we can use the generic messaging system. Upon receiving a fan greeting a given number of times, the celebrity will get creeped out. When creeped out by anything, the celebrity will have a goal of getting away from the culprit and a task to help it out with the same. On the flip side, if the fan stops perceiving the celebrity but hasn't lost the excitement yet, it'll check the last known location of the celebrity. Here we can reuse our original lookout service. If the fan fails to locate the celebrity, it'll continue its fallback idling motion. And if it succeeds, it'll attempt to greet the celebrity again. And putting that into motion, we have a slightly more dynamic scene. That's really all I have for samples at the moment, so I'll discuss a bit of background. Both the behavior selection algorithm and the perception system are heavily multi-threaded. They also contain extensive tooltips, descriptions, and custom editor tools for ease of use. They're built completely like an engine subsystem, and so they can be used with any type of games, real-time or turn-based, and it can be used for any genre of games, strategy games, or RPGs, or shooters, or even platformers. The execution system has a per-agent multiplier to make the tasks and services run more or less often, as well as to modify the ticking intervals of the planner itself. This can help out with LOD systems with regards to artificial intelligence. The CTO of Unity once said that Unity is a sandbox, that it's simple and safe. This whole toolset is created with exactly that in mind. It's very difficult to mess up, and if you do, you'll find out very soon rather than during runtime. There are actually a lot more features that I couldn't display in this video, such as the actual layering of different tasks, or the TAC map system, which is sort of like influence maps, or even a practical example. But I felt that I wouldn't be able to pack all of that in a single video, and so I'll include those samples into another video. It's all there and it all works, but it just is slightly beyond the scope of one video. I'll also try to include a less convoluted and more practical example of how this AI engine can be helpful in severely cutting down the time it takes to author AI characters. I wouldn't say the system has no room for improvement. In particular, I would love to add a domain inheritance system where one domain can be derived from another to easily duplicate behaviors between different types of agents. All that said, I'd still say this whole tool set is something I wouldn't mind using in a shipping project. And I'm really glad how it turned out, and I'm extremely proud of how many headaches it helps you avoid if you decide to use this. Well, so that's all she wrote, folks. I'll see you in the next devlog, definitely in less time than it took me to make this one. I had to throw away two different failed prototypes that each took several months of work. I had a lot of work at my day job. I also had to keep practicing other aspects of game development. I even got COVID once. And plus, Pathfinder Wrath of the Righteous happened. I'm really looking forward to the next DLC. That game took like 3 months where I did not work on any personal projects. Thanks for watching. I'll see you soon.